Okay, so with the limit definition of a derivative, all we really care about is using the information, what would that look like as a derivative? So when I look at this problem, the limit is x plus 8, the limit is h approaches 0 of x plus h to the fourth minus x plus x to the fourth, all divided by h. What I need to remind myself is this is the limit definition of a derivative where we're getting our equation. This is our f of x plus h minus our f of x. So this tells me our f of x, or our function that we care about, is x to the fourth. So this really just means what's the derivative of x to the fourth. On the other hand, when I look at the one below it, we have something similar except for we don't have x's. So this is going to be the derivative at a point, and we just need to figure out which value. Thankfully here, when I look at this, cosine of pi over 4 plus h kind of tells me everything that I need. So this tells me that our value that we're looking at is cosine of x, and we're specifically evaluating at pi over 4. And I know that for sure because cosine of pi over 4, the x value at 45 degrees, is square root 2 over 2. So I know that that is exactly what I want. So the derivative is cosine of x, and we want to evaluate it. So our evaluated at x is equal to pi over 4. Our last one here, the limit as t is approaching 1/3 of t to the negative first minus 3, all divided by t minus 1 over 3. This is also our derivative at a point just in that third option. When I'm looking at this one, things that I need to keep in mind when it's at something that's not 0, that tells me my function is right here. When we have it to the negative first, I can say t to the negative first evaluated at t equals 3, or I can say 1 over t evaluated at t equals 3. So this is the most that we're really going to need with the limit definition of a derivative. Most of the time they're multiple choice questions, so it really isn't that big of a deal. So what we're going to go with is power rule. So power rule is our kind of basics, the basis of most derivative rules. It's really our bread and butter of a lot of things. It's right up there with chain rule. So power rule, when we have an x to a power, we are going to use power rule, telling us that we are going to multiply our whatever's up front, our coefficient, by our old power, and then we are going to subtract 1 from that exponent. And if we do the limit definition of a derivative enough time, you start to see that pattern kind of unfold with different variables and different exponents. So most of the time this rule is straightforward, but sometimes we have to change the problem to use that power rule. So let's talk through these problems. So f of x equals 7x to the fourth minus 10. So this means the derivative, f prime of x, we are going to take 7 and multiply it by 4 and take 1 away. I'm going to go ahead and simplify that. 7 times 4 is 28, and 4 minus 1 is 3. This negative 10 would be like negative 10x to the 0 power. 0 times 10 is 0, so it really just goes away. It also doesn't have an x, and the derivative of a constant always goes to 0. Okay, so we have y prime, or y is equal to 4x squared plus 6x cubed minus 3x plus 4. I don't need to show any work for this. I can just write down my answer. So 4 times 2 is 8. Take 1 away, it's x to the first. Plus 6 times 3 is 18. Take 1 away, x squared. Minus 3, when it's x to the first. 1 times our value gives us our coefficient, and then x to the 0 power is always 1, so that goes away. So it's just 1 times whatever our coefficient is. And then when we have a coefficient like 4, it's going to go away and go to 0. Okay, the real thing here is how we change our values. So we need to change this because this is not x to a singular power. In doing so, we are going to use one of our exponent rules to change it to a fractional exponent. Our power always goes in the numerator, and our root always goes in the denominator. So what I'm really doing is the derivative of x to the 4/5. So g prime of x is equal to, we are going to multiply our coefficient, which in this case is 1 by 4/5, so we have 4/5 times x, and then we are taking away a whole 1 from our fraction, so it's like taking 5/5 away, which means that we really have -1/5 in our exponent. I could take time to move it back to look like what it started out as, but it really just depends on the problem and what we're doing with it to decide what is the best course of action after we get to that point. So for this one, I have not talked about chain rule, so we are not going to use chain rule. So the first thing I'm going to do for this problem is keep that 5 where it is, and we are going to cube 2x. So when we cube 2x, we have 2 cubed and x cubed. So 2 times 2 times 2 gives us 8, and x times x gives us x cubed. So even without chain rule, I can kind of do this problem. I'm now going to move the x value out from the denominator. The 8 can stay there. So I have 5/8 times x. When I move it out, it is going to be a negative exponent. So we're going to take the derivative of 5/8 x to the -3rd power. So h prime of x is equal to -3 times 5/8. -3 times 5/8 is like saying -3/1 times 5/8. So -3 times 5 is -15/8 x. When we take away 1 from the exponent, we want to make sure that we're actually taking away 1, so -3 minus 1 is -4. Once again, I could try to move this back, doing the opposite of what we did to change it to begin with, but if we don't need to, then we don't have to. Our last one. So the first thing I'm going to do is change it so we have our fractional exponent. So I have t to the 2/3, and I now have t to the -2/3. So x prime of t. So I'm going to take 2/3 and multiply it by 1/2. When I do that, I get -2/6, which can be reduced to -1/3. And if it was a multiple choice question, it probably would be. T to the negative, we're going to take away 3/3. It's already negative, so we have -2 minus another 3, so -5/3. So t to the -5/3 is a fine answer. So power rule is really our bread and butter here. It's kind of our basic rule. It's in pretty much everything, so we just got to get really good at it and remember how to do, especially the changing when we need to. Thanks for watching the video. Don't forget to like and subscribe.